Hello, everybody. My name is Aaron Fox, and I am here to present to you my final project presentation that I've titled Further Re-examining Complex Branch Predictors. This was an independent research project that I did as a part of our computer architecture course in this fall of 2020 at the University of Louisville. Moving on to the introduction. Branch predictors are a vital component in the operations of modern processors. The accuracy of branch predictors correlates strongly with the overall performance of processors, and this necessitates an efficient and accurate branch predictor in order to ensure a well-functioning modern processor. So a good branch predictor should decrease the needed energy output of the processor, avoid unnecessary complex computations that are often involved with incorrect predictions, and it should avoid computing branches that need not be processed by the processor after all, which can further save energy and time by avoiding unnecessary calculations. Unfortunately, the aim of improving predictor accuracy and therefore decrease the energy output to improve overall performance is not a simple equation or calculation. This is because the added complexities that are required to increase the accuracy often interferes with the entire goal of improving overall processor performance in the first place. Moving on to the inspiration for this project. So in past discussions for this class, I've talked about how Daniel A. Jimenez has been one of the leading branch predictor researchers in the field for decades. Jimenez has been a leading figurehead in the field of branch predictors and improving microarchitectures in general over the decades. And it is very hard to read through any form of literature on branch prediction that has been published over the past 20 years without Jimenez being one of the main point of references, or at least having his work being cited several times throughout the paper. So it therefore feels very natural to continue this trend by building off of his work on branch predictors in this project. You can see some of his expertise in this field by just browsing through his Google Scholar profile. You can endlessly scroll through his papers with various titles on the word branch predictor, a lot of plays and puns on the word branch predictor in his titles, and you can see all the citations that he's had on his work. The original inspiration for this project stems from my deep dive into his Reconsidering Complex Branch Predictors paper that was published back in 2003, and this has strongly influenced the main goal of my project. The main point of reconsidering complex branch predictors was the conclusion, which was hinted at earlier, that simpler branch predictors with fewer overheads and implementation complexities have better performance than more sophisticated branch predictor techniques that often incur more overhead and latencies as the size of the predictors grow. This led to the formation of the goal of my project, which is taken from the abstract of my paper here on the next slide. That abstract, the ending of it states, through simulations, this experiment serves to support the assertion that simpler pipeline branch predictor systems generally perform better than more complex and more accurate systems as the hardware budgets increase, proving the need for scalability and measuring performance of branch predictors over the slightly less useful metric of misprediction rate. And this paper seeks to assert this for modern predictor systems as well. So basically, the aim of this project is to see if Jimenez's conclusions from 2 decades ago still hold true today. Many changes and advances have occurred since Jimenez's original assertion, many of which have been advanced by him, actually. So I decided to set out to see how well this claim of predictor complexity not being able to scale holds up to more modern branch predictor systems that have been put out into the literature since the original penning of this paper. Going into this, I had no idea if this insertion would stand up to today's modern processor, but spoiler alert from the slide, I found that according to the data and analysis of this project, his conclusions hold up even to today's advances in the field of branch predictors. This paper works toward achieving this goal by surveying the same branch predictors that Jimenez first used in his paper 2 decades ago to compare his conclusion with modern implementations of branch predictor systems that are common in literature today. The experiments and simulations of this project therefore serve to test Jimenez's original assertion. To provide a little bit of relevant background, because most of the software programs that you write often require branching instructions that determine the flow of a program, there's always going to be some uncertainty in the execution flow of instructions and programs. So when instructions that aren't needed are executed, or a needed instruction that hasn't yet been executed occur in software, the performance of a processor can be penalized strongly because of the waiting times and wasted processor times that occur because of these issues. Therefore, a reasonable measure of prediction accuracy is required for branch predictors to help overcome this penalty. This helps to avoid these latencies and the wasted computational energy that occur because of this. There are many challenges inherent to designing a good branch predictor. Unfortunately, there is not a direct linear relationship between accuracy and processor performance, as Jimenez pointed out in his paper. In fact, when implementing the design of a branch prediction system, there are many complex relationships to consider. There are many trade-offs to consider as well when analyzing the hardware budget scalability, area required, energy use, misprediction rate, and prediction latency, which are just naming a few of the factors in this multivariate equation that arises in the design of branch predictors. And as Jimenez illustrated, the trade-off between added complexity to make a branch more accurate often leads to an implementation becoming less practical and, in fact, may worsen the performance versus a less accurate branch predictor. Therefore, a survey of both modern and past branch predictor systems is required to help analyze and evaluate some of these many variables that are required when designing branch prediction systems. And that is what this paper sets out to do. And I don't think the equation for solving for the optimal branch predictor is quite as complex as the image on the right here, but it can often feel like that to researchers in this field. Because microarchitecture designers have not always emphasized the need for scaling up the performance of branch processors relative to the hardware budget of branch predictors, there are many predictor systems currently out in the literature that maintain decreased performance for their processors as the hardware size gets larger. And one branch predictor that set out to solve this was the gshare.fast algorithm that was proposed by Jimenez. And this gshare.fast served as an alternative for designing a more scalable predictor for larger hardware sizes. This project aims to continue this exploration of the branch predictor's impact on performance and its relationship with prediction accuracy. Some commonly used branch prediction systems in the past, such as the hybrid 2BCG skew predictor, the bimodal predictor, and the aforementioned gshare.fast predictor, are all used as a baseline for analyzing each branch predictor's effect on processor performance and branch prediction accuracy. Some additional dynamic branch prediction techniques that were used more recently since the paper's been published, such as the geometric history length branch predictor, the virtualized tagged, and the neural-based branch predictors, they are all compared and analyzed with these results, all compared relative to the improved gshare.fast algorithm, with the expectation that over the 17 years, 2 decades that have passed since the original publishing of this paper, there are potential new prediction systems that provide improvements to both processor performance and branch predictor accuracy in this literature. As each of these predictor systems are surveyed and analyzed and serve as the main characters of this project, I'm going to give a short summary of each predictor system. Starting off with the bimodal branch predictor. The bimodal predictor is one of the simplest branch prediction systems known in the literature right now. It just uses the address of a fetch branch prediction instruction as a means of indexing the global history prediction bits. It then indexes those lowest bits of the address to index into the table entry, and the corresponding branch prediction bits that are output are then used to predict the branch outcome. And when the actual branch results of the software are learned, the table entry is placed with the correct results. And because of the simple nature of the bimodal predictor, this is the cheapest and simplest hardware implementation for a branch predictor system of all the systems that are evaluated in this paper. Next is Jimenez's gshare.fast branch predictor. So in reconsidering complex branch predictors, Jimenez actually designs this new predictor system, which improves upon the classic gshare algorithm. And the classic gshare algorithm functioned just like the aforementioned bimodal branch predictor, but it also recorded the global history, hence the G and gshare. The global history of these branches was used to aid the indexing of the prediction bit table, which therefore helped to provide a more accurate prediction more than just the bimodal scheme code alone. The gshare.fast improved on this gshare implementation by implementing pipelining of the branch predictor, which in effect brought the latency of the branch predictor to just one cycle. This implementation uses a four-stage pipeline where the first three stages read the pattern history table and the last stage makes the prediction. Different bits called branch present and new history bits are pipelined throughout the stages to help record this speculative global history. And the pipeline system itself works to predict a fetched branch by storing 8 2-bit counters in the first stage into an 8-entry pattern history table. The same effective steps occur for the second and third stages until the fourth stage XOR exclusive ORs the results of the shifted up pattern history table with the global history record to give the final prediction. And this allows the system implemented in gshare.fast to deliver a prediction in just a single pipeline cycle, which, as it turns out, is a very important factor in scalability of predictor systems relative to hardware budget sizes today. Moving on to the 2BCG skew branch predictor. So because non-biased and biased branches aren't uncommon in most written software today, basically every software that you guys would write would certainly have met both of these types of branches. This means that one branch predictor system alone often fails to provide sufficient accuracy because a branch prediction system alone often cannot account for both types of these branches. So hybrid branch predictor schemes such as the 2BC and GSkew predictor system allow for a higher accuracy than using just a single branch predictor scheme alone. And the 2BC GSkew predictor combines an EG-skew predictor, which by skewing the branch predictor design actually avoids aliasing, which means basically caching to the same entries in tables, just like how cache misses are avoided by de-aliasing the caching systems. And it also uses a bimodal 2-bit counter predictor, as previously discussed 2 slides ago. It combines these into 4 predictor table banks along with a meta predictor bank. And all these banks are able to use the current branch address and global history records to help determine the final prediction. So all 4 or 5 on occasions of these respective banks then vote together to help determine the final prediction. Since the global history record is often not required, only the simpler bimodal predictor is used, which improves performance, time, and maintains accuracy. But while accuracy is improved, the hybrid model is noticeably still more complex than the simpler bimodal predictor first discussed, and even more complex than fast.gshare. Moving on to more recent branch predictors that have been proposed since the penning of the original Reconsidering Complex Branch Predictors has been published is the geometric history length branch predictor. The optimized version of the geometric history length predictor allows for keeping track of very long global history records, up to about 200 bits, so that the predictions can make use of more past data in determining predictions, which leads to a higher overall accuracy. The optimized geometric history length predictor is able to still maintain efficiency in doing this by maintaining many short tables, which is achieved by nature of the geometric series that is used to determine the length of each table. So you can see in the geometric sequence I have in the photo on the right, the 2, 4, 8, 16, those are very small tables, which are naturally, those smaller tables are going to be used to hold more recent data in the shorter history tables. So the geometric history length branch prediction is able to take advantage of using many of these shorter tables for more recent branch correlations, which allows for very accurate predictions. And it must be noted that using a geometric series to determine the length of the branch predictor tables and summing all of those tables together to form a prediction proves to be a pretty sophisticated process. Therefore, while this predictor system is prominent in its high accuracy and can be pipelined to help mitigate the inherent delays, the latency involved with the complexity and the managing of so much memory can become pretty obstructive in the latencies and performance. Moving on to neural-based dynamic branch predictors. Neural-based dynamic branch predictors, such as the perceptron predictor, take advantage of simple neural methods like the perceptron, which is simply a single layer neural network. Because of the nature of neural networks, the history length of the tables can actually scale linearly with the hardware resources, which is an important factor for modern predictor systems as their respective hardware budgets are increasing. And the weights vector inside the perceptron in this predictor system, they all represent the correlation of the different branches, how related the branches are to each other. So the inputs to the network range from -1 to 1, depending on whether the respective input branches are taken. And after summing and multiplying the weights by the branch inputs and adjusting the input values depending on whether or not the predictions are correct, the output of the neural classifier will serve as the prediction of the next branch, whose output is later fed back into the input of the network again. An example of the inputs and outputs of the perceptron branch predictor can be seen in the figure on the right. Here, the perceptron has determined the respective weighted vector for each input bit to the system. And then, based on the previous 2-bit branch results and the bias results, the inputs are summed and multiplied together to provide an output. If that resulting output is greater than 0, which is the case here, then the branch is predicted to be taken. Despite the added complexity of the neural network in the system, there are still noticeable benefits of the instructions per cycle performance over more classical techniques such as the bimodal predictor. And additionally, the ability for the perceptron predictor to scale linearly in table length history size with its hardware budget proves very useful for scaling branch predictor systems up as microprocessors become increasingly large. And the sixth and last branch predictor system that we evaluate and survey in this project is the virtualized L-tag branch predictor. And this is a more recent innovation in branch predictors, which concerns the use of virtualization in branch predictor systems. The application of virtualization to branch predictor systems attempts to take advantage of the effective increased capacity of predictors in a more spread out and sleeker design. By tabulating all of the branch predictor metadata into a virtual table in a lower cache and using similar concepts of cache locality to store more necessary branch data on on-chip caches, faster data retrieval for branch information is able to be achieved while still maintaining large capacities for storing branch metadata. This virtualization was applied to the state-of-the-art L-tag predictor so that it could use a paging scheme to simulate how cache localities work with reference to spatial and temporal localities. So by extending these common concepts of locality that is well known in the realm of the caching literature side of computer science to branch predictors, the developers of this virtualized L-tag predictor are able to efficiently provide the necessary branch data with lower latencies for most needed calls, simulating how current methods of retrieving more recently accessed data from on-chip caches versus having to retrieve a larger latency for data stored way back in the L2 cache that are less likely to be needed. This scheme has been shown to improve accuracy while also requiring less overall storage, which is an important factor for the hardware budget. Nonetheless, using virtualization to replicate this core concept of computer architecture adds a lot of complexity on top of existing simpler models, which adds non-insignificant overhead and latencies that must be accounted for. Moving on to the experimental protocol. So to help compare each predictor system that we just surveyed and discussed together, some simulations were run to compare and evaluate the trade-offs of each system. Luckily, it turns out that a very useful simulation framework was already in existence. The Journal of Instruction Level Parallelism happens to host a championship branch prediction competition every year, where the goal of the competition is to use a fixed storage budget to implement the best branch prediction algorithms on a common evaluation framework that the committee distributes every year. The committee therefore provides this framework, this simulation functional infrastructure that was used to evaluate all the submitted branch prediction algorithms and therefore was used to determine the winners of that competition. These functions simulate about 21 large trace workloads, which consisted of over 30 million instructions each. And there are several different benchmarks in this traces. I think there were 7. The 2 that I found to be the most useful were the SpecInt and SpecFP benchmarks, and those are the actual benchmarks that were used in this experiment. Moving on to the actual method of testing. So I used Flexus, which is a full systems simulation software that used component interface models that helped focus on compiler time optimization and also was able to integrate all the computer architecture simulation software. And it was very useful due to its flexibility, and it was all publicly available and open sourced. The Flexus software was used to collect and gather the data that was run on the championship branch predictions simulation infrastructure. And the benchmarks of the SpecInf and SpecFP were all used to help gauge the performance of each prediction algorithm as they were readily available from the championship branch predictions infrastructure. The misprediction rate is measured for each algorithm as one metric, and the instructions per cycle of each algorithm is also considered as a more important metric to judge each branch predictor, per Jimenez's original paper recommending the most vital factor to analyze which prediction algorithm is most optimal is the instructions per cycle. And each branch predictor system was then either implemented in C++ according to the required and input and output variables of the branch competition's infrastructure, or the code was actually just taken from an open source repo and adjusted to fit the needs of the simulation framework. Each branch prediction system was then run on SpecFP and the SpecInt benchmarks 8 times each for the 16, 32, 64, 128, and 256 kilobyte budgets. And these results were then averaged for each respective benchmark, hardware budget, and predictor systems, and tabulated and visualized graphically, as you'll see in the coming slides. So yeah, next I'm going to do a dive into some of the main figures and the results and analysis and some of the key takeaways that I found from running this experiment. So this is a graph of the average misprediction rates of each predictor system. After running each predictor system 8 times for each benchmark, and where's my mouse? Sorry, I lost my mouse there. After running each branch predictor system 8 times over for each benchmark and hardware budget for each system, and then averaging the results were then tabulated. The results are summarized with the metric of accuracy via the use of misprediction rates in the figure here. And this figure, the disparity found in the misprediction rate between the 3 more recent branch predictor systems that have since been published after the penning of Jimenez's paper versus the 3 classic prediction algorithms that existed prior to and during the penning of the paper is expected, and this is pretty consistent with current literature. That is to say, the virtualized LTAG, the neural-based, and the geometric history length predictors all noticeably outperform the simpler and more classic algorithms of bimodal 2BCG skew and the gshare.fast branch predictor systems by the accuracy metric. The more sophisticated tactics of the more recent innovations, which range from a basic layer of a neural network to a virtualized cache-like system of using predictor capacity to the use of a geometric series to exploit long global history records, all allow for more innovative and precise measures that ensure a better overall accuracy using the metric of misprediction rate, of course. Also, as more hardware capability does become available, it becomes increasingly obvious that the misprediction rate improves as the global history records become larger and larger. This allows for more data to be used to base the prediction off of, which leads to the higher accuracy and lower misprediction rate. This was the case for the 2BCG skew and the geometric history length predictors, for their misprediction rate certainly decreased as a result of having a larger history record that was able to be used and tabulated to form more informed predictions based off of these larger history records. The general downward trend in the misprediction rate therefore occurs just as expected as the hardware budget increases from 16 to 256 kilobytes. Moving on to a snapshot of just the 64 kilobyte hardware budget of the previous graph. This figure illustrates how, for certain hardware budgets, different branch predictor systems may become more and more appropriate to be used. This shows the need for planning out and testing how different predictor systems perform for different hardware budget sizes. Therefore, when microarchitects are deciding on which branch predictor system to implement in their architecture, they should first consider which specific hardware budget they are using. So this snapshot of the different predictor systems at a hardware budget of 64 kilobytes shows how a certain predictor system may be more appropriate at the budget of 64 kilobytes versus other sizes, such as how the gshare.fast system is able to perform with better accuracy at that budget than the bimodal branch predictors was able to perform at 64 kilobytes. So if you contrast this with a snapshot of the benchmark performance at a hardware budget of just 16 kilobytes, then a different story starts to reveal itself. The simpler bimodal predictor system happens to perform better at that specific budget over gshare.fast, and this really illustrates how important it is for microarchitects to consider the desired hardware budget before deciding on which predictor system to use, since predictor systems perform very differently depending on their respective hardware budgets. Moving on to the realistic average IPC of each predictor system for the one cycle prediction. So based on Jimenez's research, the most important metric of this experiment concerns the actual realistic performance of the predictor systems as the hardware budget scales up using the metric of instructions per cycle. The IPC at each hardware budget is deemed more important than the accuracy as measured by the misprediction rate because, in general, the actual realistic performance of the processor is far more important than the arbitrary accuracy of a specific component of the processor, the branch predictor system. By the most important metric of this experiment, therefore, the realistic performance of the gshare.fast algorithm as it improves as the hardware budget scales up proves to be the main point of this experiment. The gshare.fast branch predictor appears to far outperform all the other predictors as the budget increases. In fact, it is the only predictor system to noticeably increase as the budget increases. This is in contrast to the other predictor implementations, which have a general negative trend in performance as the hardware budget increases. The trend of the predictor systems as seen in this figure is due mostly to the inherent complexity of the predictor systems. From neural networks to geometric series to the concepts of cache locality, there are many complexities and intricacies involved with this sophisticated yet very clever mean of lowering the misprediction rates. Because these techniques grow more complex over time with larger data sets from larger global history records, more latencies and complexities are incurred as the size of the predictor hardware budget grows. The gshare.fast implementation, however, maintains its steady growth as the hardware budget grows, as it is specifically designed to pipeline its predictions in a single cycle, which it turns out is still a necessary factor for hardware scalability today. Moving on to the realistic average instruction per cycle of each predictor system for just one cycle prediction at a hardware budget of 64 kilobytes, which is in essence a snapshot of the previous graph at 64 kilobytes. This figure, however, it provides an important caveat. When microarchitects are designing a processor, they must again deeply consider the hardware budget size that they're going to use. If they're using a size of around 64 kilobytes, for example, it appears that the more complex geometric history length predictor actually outperforms the gshare.fast implementation. That is to say, if a microarchitect had to design at this budget, the extra accuracy and predictions can be considered worthwhile at this smaller budget. However, if the designers of the processor wish to be able to scale the hardware budget of their systems up over time as technology gets better, they would likely be better off just resorting to a more stable system that is proven to scale well with an increasing hardware budget, such as fast.gshare. Diving into some of the trade-offs of this experiment, a central lesson of this experiment is that when designing a branch predictor system, considerations must be considered in the trade-off between increased predictor accuracy and the overall performance of the processor. Branch predictor designers may want to choose a more accurate system that looks to be like fantastic on paper with respect to its misprediction rate, but they must pause to consider the trade-off of using these more complex implementations that allow for this increased accuracy. If the designers are considering a larger predictor hardware budget, they would very likely be better off trading the higher accuracy for a more simple and pipeline predictor system that could deliver its predictions faster, therefore leading to better performance for a larger hardware budget. However, if the designer is working with the smaller hardware budget, they may not have to worry about the trade-off of accuracy for performance and might be able to afford using a more complex predictor system, such as a neural-based or a geometric history length predictor, which can properly be used for improving performance of the overall processor system at that size. Moving on to the final slide, just going to dive into some of the conclusions and future work. This research originally set out to question the validity of the assertion that simpler pipeline branch predictors generally always perform better at larger hardware budgets over more complex non-pipeline predictor systems, even for more modern predictor systems that have been placed into the literature since the original paper on this topic was realized. The research and data of this experiment do affirm this statement. The findings of this paper, therefore, they provide further proof and data that simpler pipelined implementations of branch predictor systems are very often the optimal choice for larger branch predictor hardware budgets. And this is an important conclusion for architect designers to observe as more transistors are able to be placed onto chips and larger, complex, more scalable branch predictor systems are needed to be proposed. It's therefore in the best interest of these designers to continue research into more pipelined implementations of the more complex branch prediction systems discussed so that they can focus on performance more than just like the red herring of prediction accuracy. And for future work, much more design and consideration into simpler pipeline versions of the more complex branch predictor systems tested in this research is needed. If these more complex systems can be simplified to use pipelining like the gshare.fast implementation, it is possible that both a higher accuracy and a scalable performance at larger hardware budgets could be combined. And this could ultimately lead to faster and better performing processors as the size of the hardware in these systems increase over time. So a future project would be maybe implementing the geometric history length predictor and pipelining that. If you can simplify and pipeline that particular branch predictor system, you could possibly combine the best of both worlds of scalable performance and high accuracy, and that might greatly improve the processor. Having said that, that's all I have to show you guys, and I am thankful for your attention, and I would like to thank you guys for the journey of this computer architecture course this fall with me. Thanks, everybody. Bye-bye.